Okay. So I get to try to paint the link between community resilience and performance-based design, and one of the links that we have is through functional recovery. So I'm really happy to be here sharing my thoughts on this. Let's see if I can. All right, so where did this idea of functional recovery come from? And it's really coming from community expectations and societal desire for something different. And so I have this quote here: "Seismic engineering is a people matter." That's from a British engineer. But I think that's something the Bloom Center has been doing since its inception. And I think so the work that we're all collectively doing on functional recovery is really a representation of really keeping people at the center of our engineering work. So I just have some examples of data we know about that people want something different or in addition to what we've traditionally provided as engineers. So this is data from Bloom Center alum Keith Porter, my friend and colleague. This is a survey of Americans living in high seismic zones. On the left, you see that more than half of those surveyed wanted modern buildings to be functional or occupiable, in addition to being life safe. And then they also did some work in showing that there is at least some modest willingness to pay for this performance. Looking at our friends in New Zealand, there's been some really amazing work done more recently in New Zealand looking at societal expectations. And this is again showing that there's a pretty high expectation of things working after earthquakes, or desire for things to work after earthquakes. So if you see the dark colors in the kind of week to month range, there's quite a bit of dark colors in the week to month range. And also looking at the differences between different types of buildings, and recognizing that there are some buildings up at the top of that list. So look at like supermarkets that don't really well fit in our traditional conception of important buildings, right? They're really important to communities, but haven't always been considered as really important in an engineering context. And in the U.S., right, there, this same idea that our communities wanted something different was an impetus for the NIST and FEMA report to Congress on functional recovery, which has really driven much of this work. So working from that understanding that we want to serve our communities in our role as engineers, I want to just briefly define functional recovery. So functional recovery is really about what does a building or infrastructure need to do in order to maintain its basic intended function. Then you could ask, well, what is a building's basic intended function? Well, it depends a lot on what it's used for and how people are using it, and that then leads to different requirements for non-structural and structural systems about what we need that building to do. And the critical idea of functional recovery is somehow between reoccupancy, which is safety, and something that's perfect, brand new, fully repaired. And so the idea is that then we can use that to inform some engineering decisions. So moving now really to the engineering. So we have this idea, we had this collective idea about functional recovery coming from these societal goals. And so how do we actually do that? So I wanted to start with some work we did at the University of Colorado as trying to put some details. So if you have a building, how do you know if it is in this functional recovery state or not? If you have a model of a building or a potential design. So what my former student Dustin Cook did, who's now at NIST, is developed a set of fault trees which really link components and building systems to these outcomes of functional recovery. So just as an illustration, this is like the highest level fault tree. So it's saying that for a building area to be occupiable, it must be safe, it must be accessible, and then the tenant unit must be safe. So there's something about global safety and local safety. And then for functional, you need occupiable, and then you also need some additional things related to that tenant unit area being functional. Now, underneath this fault tree, there's all these other additional fault trees, which are again logical statements about what you need to reach each of these conditions. So Dustin put together probably a dozen of these. I'm just going to show you one. This one is about plumbing systems, and so it's trying to link plumbing system damage to the outcome at the top where the plumbing system is functional or not functional. So the idea is that for many buildings, meeting its basic intended function may require the plumbing system to be functional, and if you need that, what are the component damage states that are associated with meeting or not that requirement that the building plumbing system be functional. And so these logical kind of fault trees are really trying to link what we were already doing in performance-based earthquake engineering of classifying damage to components and systems and aggregating it through a way to understand what is a reasonable estimation, what does that damage mean for functionality. Now, we weren't the only people working on this, so Dustin and I had the opportunity to collaborate with the ATC 138 project, and we worked in great detail on those fault trees and the assumptions underlying those fault trees, refining, vetting, et cetera, to really formally incorporate those ideas into the FEMA P58 performance-based framework. And here I have an example of a workshop that the ATC 138 team did to kind of look at some of these concepts of basic intended function. And again, bringing in that community broader input to make sure that the engineering work we we're doing is aligning with what we're hearing is needed. One important aspect of this is that the whole way along this functional recovery pathway of developing these computational frameworks, they've all been open and available and transparent. So I have on the far left, this was Dustin's original GitHub that he was developing and sharing kind of as he was going and developing his first draft of these ideas. I put Kurt Hazelton's name. SB3 has been really influential in coding it in their software, but also sharing some of the code, and then obviously Pelican here at Stanford also is providing that framework through Sim Center as well. And so I think this aspect of open science and open data has been an important part of this process as well. So what can we do with this? So I just have some examples of the types of things that if you can estimate differences between buildings in the context of functional recovery, what can you do with this? So this is again some work from Dustin Cook, looking at differences between walls and frame buildings, showing, first of all, large variation in functional recovery between buildings and across realizations, and then also differences between structural systems, so some potential benefits of a stiffer system that reduces drift-sensitive components. On the right, we have the distribution of damage associated with functional recovery in his assessments. And the thing I just wanted to flag there is that the components that you see coming up as important for functional recovery are not the same components that come up if you look from a repair cost perspective. So this is one of the benefits of looking at functional recovery. If you ask the question, which of my damage is going to be most expensive to repair, you get some list of things. If you ask the question, which of the damage is going to be most consequential for me in terms of recovering, you get a different list of systems, and that might help us be better designers and engineers to know what that list of systems is. One of the other things that Dustin did is he kind of looked across buildings and across realizations and observed this kind of bifurcated outcomes for recovery. And so you can get fairly quick recovery. You can also get fairly long recoveries. And the thing I want to emphasize there is that whereas repair costs are really an aggregation of all the things that happen, functional recovery is kind of a bunch of things that are in series, and if one thing doesn't happen, then it's going to take a long time to repair. So if you have damage to your HVAC system from a few components, that can lead to long repair times, even if it doesn't necessarily lead to large repair costs. As several of you know, I always like to work on existing buildings. So my research group has also done some work on existing buildings. So here we were saying, well, what do we get? Do we get functional recovery with some of the retrofit strategies we've explored in the past? So here, the orange curve is a real existing building, and then the blue and the green are retrofit strategies. And what we found is that we looked at a bunch of retrofits that had been done with life safety in mind, and we found that some of them, like those shown here, actually provided pretty big benefits in terms of functional recovery. So even though the engineer wasn't working on functional recovery, the reduction in collapse risk, the stiffening of the building actually provided quite a bit of functional recovery. But we also found cases where that was not true. So here we have an annualized measure of repair time or recovery time on the y-axis, several different buildings, frame and wall buildings. That's what the F and W stand for. And you can see that as you move from the lightest orange to the darker orange, in some cases there's not a very big difference. And so those are retrofits that were done for other reasons, and they really didn't provide much of a benefit in terms of functional recovery. And one of the reasons we see that is because there's a disadvantage of stiffening in some cases, of creating a lot of accelerations and really increasing acceleration sensitive damage. So needing to find this like trade-off between or the ability to find solutions that reduce both drift and acceleration sensitive damage if you really care about building function. Turning now to some work by Tayo Opabola. He was looking at, well, if we have buildings designed with different strategies, what differences do we see in functional recovery? And this is really coming from, in New Zealand, they're looking at designing for repairability or damage control by limiting deformations in components as the design philosophy. So these 4 different buildings have different limits on that repair, on that deformation that they're allowing in the critical components. And so the ones at the top have a fairly high level of damage control, the ones at the bottom have less. And so if you look at the y-axis values, you see that as they implement this structural design intervention to limit deformations in structural components, they're seeing in turn, when they assess functional recovery, a benefit from those design strategies. This work is from Carlos Molina Hutt, who's now at University of British Columbia, but was previously in the Bloom Center. And I wanted to show this too because it's just showing that if we think about functional recovery, we can also think about some of these impeding factors and that impact the time. So I mentioned that Dustin, and we think about functional recovery, we thought about mapping components to functionality damage state. We also thought really hard, and also with the ATC 138 team, about what are those impeding factors, how long do they take, what factors affect those impeding factors. And so here's some work from Carlos and his team showing the same building in the 2 cases, but on the one that's labeled recovery planning, they considered faster inspections, faster permitting times, an engineer and a contractor on retainer, and they're showing the benefit on the x-axis of some reduction of time. So by thinking about functional recovery, not only can we think about kind of the structural design interventions, but also the other interventions we might make to help our communities recover faster. Another example from Ann Holsey is looking at cordons. So she was looking at functionality in community sense. And if you look at the 2 maps, the difference in the orange and the blue is really showing when cordons are mattering for us getting function. And so again, thinking explicitly about function and developing ways of quantifying it is allowing us to interrogate not only kind of policy-making decisions, but also building design and management strategies. So some ongoing work right now is working to develop functional recovery design provisions in a prescriptive sense. So here I'm highlighting some work from Kristen Blows, and what they're doing is they are looking at what drift limits and what R values might be needed to achieve functional recovery. So here they have RFR, which is a R value designed for functional recovery. They have a drift limit that's for functional recovery. So looking at the potential for stiffer buildings and also stronger buildings, and seeing the colors then are a part of the functional recovery measurement that they're calling safety critical damage. And so they're looking at what combinations of strength and stiffness can give us that functional recovery state, and then really using that to help inform proposals for design provisions that we can incorporate into our building standards. So what's next? So I think, we will hear a lot of these things probably going forward. I have here some work from Omar Issa, who was at Stanford. I think there's a real potential for machine learning. There's some complexity in these models that we might be able to leverage. And that's an example on the right is from Omar showing that. I think we really can do more to link the community scale work that Jack was showing to these individual building functional recovery assessments. We're really being driven by that community scaled, that community desire. And I think we all know there's a link, but I think we could do more to be more explicit about that link. There's obviously a lot of challenges with existing buildings and thinking about how we can make some of those choices. I think in practice, we know, and that Greg Luce showed a bunch of creative, resilient designs. We need more of that. A lot of those are going to be our solutions as opposed to taking the same systems and just modifying them. And we also need advanced building products for non-structural systems that can meet some of these demands that we're looking at. Finally, I've been working a lot on standards for building standards that reflect functional recovery. And I think that's just so important for helping us make sure that functional recovery isn't something for well-resourced communities and organizations and people, right? I think if we're really interested in community resilience, one of the ways that we help this be a tool that can be used by many is providing the simplest possible strategy we can to get those designs done effectively. So I apparently have no pictures from my time at the Bloom Center because I didn't have a phone. I didn't have an iPhone, but I was thinking a lot about like what else we need. And I think we have to remember how we got here, which is we got here from communities wanting something more different. And we got here from our collective desire to do that. And so as we continue to move forward, I think, we really need each other. We need to listen as well as talk and listen to our communities and to each other to make sure we're really staying focused on that goal, which is that serving communities. So to conclude, I really think we can help communities have the post-earthquake and eventually post-disaster outcome they want, and that these tools are really can be really useful for them. And so I'm really happy to be with all of you on this journey. So thank you so much.